So basically, I want to present you some of my research that I've done over the past couple of years, mostly at UNSW in Sydney as a postdoc, but also now continuously here at CSIRO Mineral Resources for the past year or so. In my research, I was mainly investigating some very intriguing, some very ancient microbial structures, and namely the stromatolites from the 3.48 billion year old dresser formation in the Pilbara Craton of Western Australia. And I will show you the results that really allow us now to see for the first time that these structures are really a benchmark for the oldest evidence of life on the Earth. But first of all, I want to start from the very basics. Not sure if everybody is so familiar with stromatolites. So, yeah. So what is actually a stromatolite? A stromatolite is in simple terms microbially formed rock structure. So we know them, for instance, here from Shark's Bay of Western Australia to the lower left. They are usually these rounded or columnar layered laminated organogenic sedimentary rock structures that formed by diverse groups of microorganisms like autotrophs, like photosynthesizing bacteria, together with heterotrophs like sulfate-reducing bacteria. And the key feature in the formation of the stromatolites is the nature of the biofilm. So a biofilm consists of microorganisms plus their secreted exopolymeric substance in which they live in. And this is a very sticky material. And so due to the sticky material, I hope you can see also my mouse when I show you. So owing to this sticky material, it likes to collect mineral grains or even promotes mineral precipitation to form layer by layer the stromatolite structures. Nowadays, however, stromatolites are intrinsically rare. So we know them, of course, from Shark's Bay of Western Australia, but they are always restricted to ecological niches that are actually more or less hostile to higher life forms like animals. And so they really have peace where they can flourish. And so we can find them in the hypersaline waters of Shark's Bay, of course, but also other examples in the Bahamas to the lower right. However, while they are nowadays quite rare, they have been most likely been, or we have evidence, or we know very well, that they have been the dominant expression of life in earlier Heian to Precambrian times. And so there's this, for instance, this famous picture from the Smithsonian Institute where the painter was imagining how early life could have looked like. Of course, volcanogenic environment, marine environments, up to shallow marine environments, and then exposed land surface, of course, with abundant hydrothermal activity, magmatically driven. And here these stromatolites, these noddy structures have been formed. And we will see actually that this picture here is actually one-to-one what we see in the dresser formation, in the dresser formation and the formation of the stromatolites. But first, we should try to better understand actually how can we recognize fossil stromatolites in the rock record. Of course, over the past decades, they have been studied, and there are many, many textural features that are diagnostic or typical of stromatolites. So we need to gain an understanding of the morphology. Are these thin planar stromatolites, stratiform stromatolites, dome-shaped stromatolites, even what are internal growth forms of a stromatolites, flat laminated forms, or we see internal domes or columns. And then also what is the laminar shape, flat or undulating, wrinkly laminated. One other important factor, or one other important thing is that we should also try to understand what is or what has been the physical background, the geological background in which the stromatolites have been formed. So let's have a look at the Shark's Bay, for instance. We see nowadays, we see a shallow marine environment, and very quiet. We see these microbial features, and we see these microbial features surrounded by just flat, rippled sediments. And that tells us already something, because we have here just an ordinary physical process and suddenly a biological process that forms these columns or domes. And with this knowledge, one can really try to better understand the formation of ancient stromatolites and if they are really ancient stromatolites. So to the right, if we have some intriguing columnar structures, for instance, and we even potentially see in between these columns just plain rippled sediments in a physical process, we can start to think whether this could be indeed a microbial structure. So with that in mind, let's have a first look now at the stromatolites of the Dresser Formation. As seen here, some beautiful examples. What you see first of all here from surface is that the stromatolites are extremely ardent. So they usually have this rusty red color, so very typical what we see in the Pilbara. And what we see is here to the lower, to the upper left, these flat stratiform wrinkly laminations that are quite typical of microbial features. Also to the right, we see some photomicrographs where we see these flat-bedded stromatolitic forms, or sometimes even wavy. But while these textures are similar or can be microbial, they are not necessarily diagnostic. So it can be also sometimes stromatolitic forms may be confused with abiogenic mimics, abiogenic mineralogy. And so these rock structures have been now known since almost 40 years, but up to the recent, there was really quite a controversial discussion whether these are really microbial features or just abiogenic mimics. And so for the last 4 years and continuing now, I was studying these stromatolites, and I was writing a couple of papers which key evidence for life that I want to summarize in the following. And some of these results really gained some good attention in the media, even Fox News, although Donald Trump was not covering it. Well, also he did, but that's life. So, and we should, at the beginning, however, we should now step back once more and just have a broad look at the geology of the Dresser Formation to understand where they are located. The stromatolites are located. So they occur up there, of course, in the Pilbara region, at the so-called North Pole locality. We see here this geological map of the North Pole, with the Dresser Formation indicated here, this narrow light blue band, and sitting just atop ordinary basalts and komatitic basalts. The Dresser Formation itself, as we see in the following, is mainly a succession of shallow marine to sub-area metal-sedimentary rocks that were strongly influenced by syl and post-depositional hydrothermal activity. The stratigraphy of the Dresser Formation is well resolved also in a drilling initiative in 2004. That is also very important for my study, as we will see later on. There we see the stratigraphy. Of course, we have the basalt basement, and then, of course, the overlying Dresser Formation, starting with bedded white black chert or gray chert. Then, very important, the so-called chert barite unit that hosts the stromatolites in hydrothermal and sedimentary strata, so together with carbonates, sandstones, and conglomerates. But of course, everything that we can see in the drill course, we see also just by wandering around in these remote areas of the Dresser Formation in the middle of nowhere almost. So what we can find very ancient metasedimentary rocks, like here this so-called anchor chert layered zebra rock that likely represents a shallow marine environment with evaporative cycles to form chert, anchorite, etc. Then we can see cross-bedded and rippled sandstones, and of course we see these very famous stromatolites. However, in the Dresser Formation, we have, of course, also strong hydrothermal activity, or we had strong hydrothermal activity. And this is evidenced by, for instance, here we have the basalt underlying the Dresser Formation, strongly altered. We see abundant hydrothermal dikes that really transact in multiple vein systems the underlying basalt, but that terminate actually with the Dresser Formation or grade actually into the Dresser Formation. We see these chert veins or chert and barite veins. And these, particularly the chert and barite veins, they really grade into the chert barite unit that can also host the stromatolites with these sedimentary units. And so we can have once more a look back to this picture of the earlier here on Earth, and then we start to see already this is really a very the dresser formation is really a very good example of what is drawn in this picture here. And one idea that was also developed by my colleagues at UNSW was potentially that dresser formation is something like, or formed in something similar like an ancient megacaldera, a collapsed ancient megacaldera with potentially some modern analogs like White Island in New Zealand. So where a shallow marine environment was formed, where the stromatolites grew in vicinity to hydrothermal activity. But now let's really finally delve into the stromatolites, into my work. So let's again, you see here the stromatolites from the surface outcrops, usually strongly altered here in dominantly hydrothermal mineralogy with chert and barite. And we see that on the surface, these stromatolites are very strongly altered. No primary mineralogy, no primary petrography whatsoever. However, this is very different in the drill course that I was telling, or that I've showed you earlier. This drill course intersected exceptionally well-preserved stromatolite structures, you see at the bottom, coming from below the weathering profile in the dresser formation. So they experienced no weathering whatsoever, and they preserved primary petrography mineralogy. And there we see that actually the ancient dresser formation stromatolites have been actually primarily composed of pyrite, now altered, of course, on the surface to iron hydroxide. So sulfidized pyrite plus phenolphthaleite, and of course also a little bit dolomite. But this is actually quite unusual if you think of more modern stromatolites that are usually just dominated by carbonates and actually not sulfides. And so I was really studying these stromatolites at multiple levels, multiple scales with various techniques as we see. But first of all, let's just have a look at now this picture of this stromatolite from drill course. What can we just see from the texture-wise evidence for life? Of course, we see that these rock structure or these structures are embedded in what appears to be quite flat-bedded hydrothermal-sedimentary strata. So a physical sedimentation process. But now suddenly we have these features, these almost like columnar or dome-shaped features at the bottom with in red here with upward branching digitate structures, and overlaying by like columnar features like weird laminated features. That really tells us we had here something acting against the physical sedimentation process, so very likely biology. But with that alone, I was not happy, of course. I really wanted to understand with multiple techniques the biogenicity of the stromatolites that I was doing over the past 4 years. And I was doing this multi-scale investigation for chemistry, mineralogy, etc. One particularly important tool was just ordinary scanning electron microscopy, because it really allows to do microtextural and micro-mineralogical examinations at multiple scales, from millimeters or centimeter scale down to the nanoscale even, as we will see. And the main tool that I was using was so-called backscattered electron imagery, as you see to the right, of such laminated and digitate structures. And these backscattered electron images, I will show you many more in the following, so we should get understanding right now. They are basically chemistry sensitive. So in dark, usually minerals or elements with that have a low mass. So for instance, chert and carbonate, which is silica and carbon. We have the pyritized and stromatolites in intermediate gray, because iron is more heavy, of course. And then we have very bright mineral grains, very heavy minerals, of course, barite. And so I was studying now these stromatolites down to the nanoscale. And in particular, let's have a look at these. We see these upward branching digitate structures here at the bottom. And we will see in the following that I was looking at these structures down to the nanoscale to really look into microtextures. And already by doing that work, I was figuring out something very, very crucial and very, very important. Namely that the genetically earliest parent generation, or sulfide generation here in the stromatolites, we see here outlined in red to the left, is actually a very distinctive, this is what you see to the right now, a very distinctive nano-porous, almost spongy pyrite texture. And this is quite unusual if you think of pyrite usually forming individual grains, etc., or massive grains. And we see actually also massive pyrite at the borders of these digitate structures, but the heterogenetically earliest phase is this nano-porous pyrite. And this is really intriguing because I was doing also the Raman spectroscopy analysis of this earliest pyrite generation that really has shown actually that these nanopores of this pyrite are essentially filled, or all this nanoporous pyrite is strongly enriched in thermally major, primary, very ancient, apparently organic matter. This organic matter is very typical. See here in Raman spectroscopy, showing these typically sharp bands of the DNG band that really tells us this is very old, very thermally major organic matter. And this is really a crucial observation because it shows us that all these nanoporous pyrite, here indicated in red to the left, is enriched in organic matter, and in its formation requires apparently pyrite precipitation onto an organic matter template. And so now you can start to think, what could be such an upward branching organic matter template? Of course, a biofilm or biogenic structure. So this is really a first smoking or strong evidence for biogenicity of these stromatolites. But then in the next step, I was interested, okay, how could this organic matter in this pyrite actually look like? Is it just randomly dispersed organics, or could we even find organic matter remains or coherent microbial remains? And for that purpose, I was then using so-called nitric acid etching. So etching the pyrite with acid. The pyrite is strongly dissolved by this acid, but not organic matter, and so the organic matter structures are untouched and come to the surface. And what I was finding was really intriguing, because entombed with these in these etched nanoporous pyrite, I found then these very coherent, multiply twisted, very complexly formed organic matter structures. Like here, these filaments, again, we have here backscattered electron images, so all the organics are here with dark features. So very complexly twisted filaments and strands of organic matter. Here another example of a little bit more, still more pyritized organic matter, but you can see here clearly there are apparently two cylindrical, almost tube-like structures that start to fray into individual organic matter filaments. Many more examples. Here, this frayed organic matter strand, clearly sitting within the etched nanoporous pyrite that is so important, as I mentioned before. Here, again, fraying out or splitting into individual strands. Another picture, this time with secondary electron imagery, that is just topographical information, but we can clearly see we have some very intriguing, coherent organic matter sheaths that here, after etching, directly come out of the etched pyrite and also wrap and transgress pyrite grain boundaries. Then finally, my favorite feature actually. Again, here we have sphenoidal filaments. You see in dark is all organic matter. You see also to the lower right, you see a Raman spectroscopy map of the organic matter. So clearly filamentous structures that almost appear to follow along a cylindrical axis from the lower left to the upper right. And also, for instance, transgressing here grain boundaries of pyrite, that really tells us that these are really the earliest features of these rock structures, because pyrite was nucleating over them. So you see that here outlined, for instance, such a grain. So then the question, of course, was, what can be these structures actually? So for that purpose, I was then really trying to study and understand how microbial remains, for instance, in modern stromatolites look like. And so I was browsing the literature, and what I was finding actually is pretty intriguing. Namely, you see the lower picture from the study of methane stromatolites, for medium filamentous bacteria, photosynthesizing bacteria, that such degraded bacteria leave behind these deflated organic matter sheaths, as you see in the lower right picture. And this is really one-to-one what we see actually within the Dresser Formation stromatolites. You also see to the lower left such bundles of individual degraded filaments, bacteria filaments. And this is almost very similar to what we see in the upper left in my stromatolites and our stromatolites. This really tells us that we really likely, or we apparently deal here with the words, so far oldest microbial remains found, these within the stromatolites of the Dresser Formation. And this provides evidence that these stromatolites eventually formed by such very similar filamentous bacteria. But also one intriguing outcome of that, or if you think further, that means also that how could we have such a perfect, almost not perfect, but very well preservation of these microbial remains? Well, it must have been that they have been preserved by rapid sulfidization. So very quick and very strong pyritization and sulfidization. And this will also get important in the following. But before that, I want to show you some additional feature that I found together with the organics in the stromatolites, another key evidence for life. And this is this very unusual barite mineral precipitates. You see these almost orbicular, ball-shaped barite precipitates, always in association with abundant organic matter. You see here in very dark gray or almost black organic matter, and of course sitting together with this etched nano-porous pyrite. Here a nanoscale image where you see the internal texture of such very tiny orbicular barite precipitates. You see a nano-porous core, or almost like a amorphous nanocrystalline core, and then you see somewhat like a shell morphology on the outside. Here you see a different example of a little bit different orbicular barite precipitates, here a little bit more smooth surface. Here again, such a high resolution image to the right, a little bit different imaging technique, where you see clearly these orbicular precipitates, sometimes partially hollow, it's almost like nano-framboidal pores. And so now you might ask, why are these precipitates so important? Well, if you think of barites, for instance, hydrothermal barite and whatsoever, or the genetic barite, we usually form hydrohedral or blocky grains, but not usually or mostly not such spherical barite precipitates. And in fact, micro-spherulitic barite morphologies are very indicative of barite precipitation in the presence of abundant organic matter. So organic matter promotes barite nucleation, but inhibits growth of barite, and so forming these crystalline rounded aggregates. And indeed, there have been a couple of laboratory experiments using modern-day marine microbes. You see the lower right. So where they were feeding just modern-day microbes with barium and sulfate and looked what is the outcome. And in fact, you see almost one-to-one the same features. You see these orbicular barite precipitates, sometimes still partially hollow, as in our case, then continuously more well crystallized. So this really tells us that these could be actually potentially even biomineralization in the stromatolites. But then let's have a look now back to the sulfidization of the stromatolites. In order to understand the formation process and the sulfidization process that apparently promoted the preservation of organic matter remains, or what look to be microfossils, I was then also interested in studying the chemistry, and I'm still doing that right now here at CSIRO, the chemistry of these microbial features. And I was mainly doing that with synchrotron radiation XFM elemental mapping that was doing in synchrotron, but I also do that here now with the Maya mapper at CSIRO Mineral Resources in Perth. And these analyses have really shown us, and really showed that all the stromatolite, the parent of the stromatolites and the sphalerites, is really heavily enriched in various transition metals and metalloids. So you see here, for instance, in a map of nickel, qualitative map, you see this strong enrichment in all these, for instance, digitate structures at the bottom, upward branching, but also particularly you see a strong enrichment in these wrinkly laminations sitting at the digitate structures. Here another example of such a sulfide column, stromatolite sulfide column from such elemental mapping. Here a tricolor elemental map, where everything in color here is actually sulfide. So it presents a columnar structure, columnar sulfide structure. So you see nickel in red, zinc in blue, and arsenic in green, for instance. And this technique was really, really helpful to even understand now individual growth stages of the stromatolites. So you see here these repetitive cycles of nickel, also like blue sphalerite zinc, nickel zinc, etc., etc. And in the left image, outlined with the arrow, you see even unconformable overgrowth relationships. And here in the right image, you see the same again, just with nickel and zinc. Where you see among this overgrowth relationship, you even see an accumulation of zinc in wrinkly laminations. So all that really tells us that these elements must have apparently been accumulated almost, or it looks like, during stromatolite growth, so concomitant with stromatolite growth. This is also telling about the pyritization process, because that fits very well with the idea that we had this early stage pyrite precipitation to entomb these organic metalloids. Then I was not only doing XFM elemental mapping, I was also in localized areas. I was doing elemental mapping with laser ablation ICP-MS for various trace metals and trace elements and minor elements. For instance, of course, with nickel and zinc, we have we see the same features result, these wrinkly laminations of the column, but also other elements like cobalt or copper and antimony provide really very important information. Because this is what we see, for instance, here in the next slide. So let's have a look now into into this cobalt map, for instance. Here it is a rear outline marked with this rectangle. What you see actually suddenly is within wrinkle or these laminated column structures of the stromatolites, you see almost like upward growing, upward branching, sometimes columnar structures. And when you closely look here with the white arrow indicated, you even see almost like upward convex lamination. That is really, really telling of a stromatolite form. And of course, that also is important because it shows these upward convex features, of course, etc. And also another important fact here is to understand that all these element accumulation here of cobalt, for instance, all the colors here in the map overlap or are hosted with this organic matter-rich nano-porous pyrite. So all what we see here, all these digitate structures and apparently microbial structures are actually organic matter-rich nano-porous pyrite hosting these microbial domains. So it fits very well this picture together, that these are really microbial structures. So, but now the question is, why are these accumulations so important to understand biology? Of course, we see, due to this analysis, we see school book-like microbial fabrics of organic matter-rich nanoporous pyrite enriched in transition metals and metalloids. It really allows to decipher internal microtextures or microstructures, microbial structures, and it allows to even further explore growth stages of the stromatolite. And then the question arises, why do we have actually the strong accumulation of these transition metals and metalloids in these stromatolites or in these microbial fabrics? Well, there's a very simple explanation for that. Because all these elements have usually a strong affinity for organic matter. Or in other words, organic matter really likes to bind all these transition metals and metalloids like nickel, zinc, cobalt, antimony, etc., etc. And even more intriguing explanation could be that we have had potentially even influenced by microbial utilization. So, for instance, it's very well known that nickel and zinc are key elements for microbial metabolism, for instance, for prokaryotes like sulfate-reducing microbes. And such sulfate-reducing microbes could have even contributed to the sulfidization of the stromatolites. So these are now really the key evidences for stromatolites biogenicity, and I would like to summarize now everything together. So what have I shown you? So we are showing you that we have here really the dresser formation was a hydrothermal influenced shallow marine, potentially even hot spring dominated subaerial environment, where the stromatolites were growing in close vicinity, apparently hydrothermal activity, phototrophs like ancient photosynthesizing bacteria forming these ancient microbial mud structures. Then I've shown you what we believe is really smoking gun evidence for the first time for the biological windshields of these stromatolites. So we have microbial remains entombed within the earliest formed organic matter-rich nano-porous pyrite of the stromatolites. And all these features are also associated with this micro-spherulitic pyrite precipitates. So it's really telling for biogenicity in our opinion. And we have put forward also then in the papers that this is really like a benchmark for life on Earth. Then something else is, and this I could not tackle very much now in this talk, simply because it's also a bit complicated, is the question, why do we have the strong sulfidization of the stromatolites? Of course, we have a strongly hydrothermal influenced environment, and there's certainly a contribution of hydrothermal fluids to this sulfidization process. But we have done also sulfur isotope analysis of these structures of the pyrite, so in situ sulfur isotope analysis of the pyrite, with really isotopic evidence that we potentially have also influence here by sulfate-reducing bacteria that reduce sulfate to H2S and then to contribute to the precipitation eventually of pyrite. And lastly, I've shown you that we have these very strong accumulations of various transition metals and metalloids directly sitting within microbial structures. And I've shown you that the likely explanation is that these elements were accumulated onto organic matter due to the affinity of organic matter or the affinity of these elements to organic matter of biofilms. And then also, for instance, elements like nickel may have been concentrated from seawater, and other elements like zinc, hydrothermal elements that like to concentrate from hydrothermal fluids, for instance. And that all fits together with this picture of ancient stromatolite growth in such hydrothermal influenced shallow marine volcanic setting. Okay, that was it. I hope you enjoyed the talk, and I hope it was informative. And if you have some questions, please feel free to ask.